So today we're going to practice describing the region R with what's x between and what's y between. Last time on Calc 3, we talked about the rules for setting up an iterated double integral. The last integral only gets to use constants. Early integrals can have functions of upcoming variables. To reiterate what we mean, when I say the last integral, if I have a dx dy integral, dy is the last integral. Sometimes I'm going to say the outside integral or the outer integral, because it's like the one on the outside. Whichever way I phrase it, the last integral that you go through, that one has to have constants. So y goes from c to d. But early integrals can have functions of upcoming variables. So my x integral can go from a function of y to another function of y. This is where we're going to be describing the curvy bits of the region, if there are any curvy bits. But we're going to say what's x between and what's y between. The other order, a dy dx integral, notice that I have x is between two constants, but my y integral can be between two functions of x. X is the upcoming variable. Early integrals can have functions of upcoming variables. The last integral only gets to use constants. Early integrals can use functions of upcoming variables. The last integral only has constants. Yesterday, we described a rectangle, and it didn't matter what order we went in, because a rectangle is just an interval on x cross interval on y, or interval on x by interval on y. I shouldn't say cross, it's not a cross product. So what we're going to do now is I'm going to break up that region with some curve. So I'm going to look at part of the region. So for example, I think yesterday I was using 3 and 9, so I'm going to continue that. So I set up a region where y was between 0 and 3, and x went between 0 and 9. What I'm going to do now is I'm going to divide this region up with some function. I'm going to start with the easiest thing to do, just connect two corners. There are two regions. I'm going to call R the upper region. I'm going to call that R1. And we're going to describe a definite integral over R1. Now, this is on the floor. This is stuff on the floor. I got this triangle, then there's some function sitting up here. I put the function pretty high because it needed to be behind the camera so it didn't get in the way. Originally, I'd set it down here. You couldn't see what I was writing. So I just added 5, and that was enough to take the surface and move it above the camera. So it goes pretty far up. We're not worried about that part, because even though I haven't told you how to find partial antiderivatives, you already know how to find partial antiderivatives. So I don't have to. So I ain't gonna. Eventually. Sort of. So R1 is going to be this upper triangle. Here is the region that we care about. I'm going to set up two double integrals so that we can evaluate them as iterated double integrals. Over the upper triangle, I can set up a dx dy integral. And then afterwards, we can set up a dy dx integral. Notice that I listed the rules with last integral first because that's the easiest one to write down because we have to use constants. In this dx dy integral, y has to be between constants. We ignore any kind of shape. We just want where the y's are. Y goes from 0 to 3. The reason the rules are listed last integral first, that's the easiest one to set up. So do that first. What we're going to do is pick a typical y value and then figure out what's x between. So what we did here, first, set up the last integral. Set up the last integral first because it's easiest. That was not a good choice for a whole sentence. Now what we're going to do is, since we did y first, we're going to choose a typical y value and say, what's x between? We're going to choose a typical y value, and we're going to say, what's x between? Here's a typical y value. X starts off at the line and ends at 9. Those are, for that y value, those are the x's that we want. We start off at the line and end at 9. It's comparable that those rhyme. It just sounds stupid. It sounds like I intended for them to rhyme. Dang it. So we pick a typical y. We start and we just say, what's the lowest x value that we see for this y value? Starts off at the line and ends at 9. I'm just going to write that in. Line to 9. So what we need is we need the equation for that line as a function of x. Sorry, with x as a function of y. So that line is easiest to write. Our training for writing lines is y as a function of x. So this line is going to be y starts off at 3 and decreases by 3 every 9 units from 0. Y is 3 when x is 0 and decreases by 3/9. As the rise is -3, the run is 9. We can simplify that to 1/3 when we solve this for x. This is not what we want. We want x as a function of y. So x is going to be, let's see, multiply by, I'm going to make this 1/3. multiply by 3, and so we'll have y minus 9 minus x. Y. So I can use functions of the upcoming variable. I need to write the line as a function of y. So I'm going to write the line as 9 minus 3y. That's where my x starts, and my last x is at 9. So instead of writing line, I'm going to write 9 minus 3x. Y. See, I keep doing it. Now it's a thing, and I can't stop. So I'm going to write x equals 9 minus 3y. That's the line. And so we start at the line and go up to 9. Or you should say this is a line along a typical y values. We don't get away with just writing 1 when there are 2 available. So I have to write a dy dx integral. The last integral only gets to use constants, so it's the easiest one to set up. In this region, x goes from 0 to 9. I don't worry about anything else. I just look where the region is between on the x. X goes from 0 to 9. Now we're going to pick a typical y value. Sorry, we're going to pick a typical x value and answer what's y between. We'll pick a typical x value and say what's y between. Y starts off at the line and ends at 3. I can't just be writing y equals line. I can't just write the word line. I need some function of x because I get to use functions of upcoming variables. So I'm going to replace line with y equals 3 minus a third x. That's the y as a function of x description of the line. Any questions? I've taken this rectangle and cut it in half to an upper triangle and a lower triangle. So for practice, not right now, go later, think about what the integral would be, both dx dy and dy dx for the lower triangle. So first, and then here's what we did. Any questions? One of the things that we're going to need to do is look at some function y as a function of x and be able to rewrite that as x as a function of y. Same thing. Let's set up a double integral for this R3. Now I've got this line going the other way. As a y function, this line would be described as y equals 0 plus 1/3 x. But as an x function, I would say x is equal to 3y. So multiply by 3 and x equals 3y. So when we say line and we need x as a function of y, x equals 3y. If we need the other one, when we say line, we need y equals 1/3 x. This one is a little bit different. In the previous one, the typical the x's start at the line and go to the end. It's for a typical x, we start at the line and go to the end. But it's different in this case. So take a minute, think about the double integral of f of x, y, the dx, dy, and the double integral of f of x, y, dy, dx. A little printing press style. Just going through one color at a time. Which example? Yeah, that's 1/3 x. So y is equal to 1/3 x is just a description of y. Oh, we only get 2 right now. So let's set up these double integrals. The easiest thing to do is the last integral first because we only get to use constants. So if my y integral is my last integral, y is between 0 and 3. Now we pick a typical y value. And we say, what's x between? Here, x starts off at 0 and ends at the line. So x starts off at 0 and ends at the line, the x description of the line, which is 3y. So this would be the integral from 0 to 3y dx, then the integral from 0 to 3 dy. For the other integral, if it's a dy dx integral, we should do the x's first because the constant one is easiest. So the x, if we pick a typical x, y starts at the line and ends at 3. So for this typical x, I'm going to shade in where the typical x value intersects with the region. So the y starts off at the line and ends at 3. The y description of the line is 1/3 x. And we end at 3. Let's connect the same 2 points, 0, 0 and 9, 3. But this time, instead of with a line, let's connect it with a parabola. So instead of this upper triangle, now it's been dented. So this parabola, let's describe with, I made it sideways, so y is x squared. If I need the other description, like I will for my dx dy integral, x will be the square root of y. If we're solving for x, I'd need to write plus or minus, but clearly I have the positive square root of y. This is the upper part. Write 2 double integrals for the integral over R5 of generic function f of xy. No, on your notes. Piece of paper. dx dy, dy dx. No. Oh, yeah. The wrong one. In other versions of this problem, I have taller rectangles. I forgot that was the other reality. Did it again. The outer would be the same, but for for R2, we would go y would go from 0 to 3, but x would go from 0 to the line. So 0 to 9 minus 3y. For the lower triangle dy dx, x goes from 0 to 9, y goes from 0 to 3 minus 1/3 x. So the line would be the end point, the end, and 0 would be the start for R2. All right. We're still playing the game. What's x between? What's y between? That's how we do iterated double integrals. But for now, for the rest of the time, please find these 6 partial derivatives. Kind of fit all on one screen.